Okay, I believe we are on the last two for the physical optics. So if I can get this to let me be able to use my pen. Come on, come on, come on. All right, hang on a minute. Okay, now it's cooperating. All right, it says, your teacher gives you two speakers that are in phase and are emitting the same frequency of sound, somewhere between 5,000 and 10,000. She asks you to determine this frequency more precisely. She does not have a frequency or wavelength meter in the lab, so she asks you to design an interference experiment to determine the frequency. The speed of sound is 340 in that lab room. From the list below, select additional equipment you will need to do your experiment by checking the line next to each of them. Okay, so I want a sound level meter so I'll know when I've got minimums and maximums. I want to have a meter stick. I want to have a tape measure. And that's all I need. And some people would select stopwatch because you think about speed as distance over time. Don't even go there. Okay? All right, draw a labeled diagram of the experiment you would use. On the diagram, use symbols to identify what measurements you would make. So it's going to be kind of like what we did last time. So we're going to have a speaker and a speaker. And this distance from here to here we're going to call D, how far apart they are. And then we're going to have this line. There's going to be a screen right here. And really don't even need a screen. We just need a line we can walk along. Mine's not very straight, but you know, if I were a better artist with this little tablet, it would be better. So that's my Y, where that would be the maximum, and that would be the next maximum. Alright, and I would want to know, more than likely, this distance L right here. So I would use my meter stick to measure that. I think I'm pretty good to go. Okay. Briefly outline the procedure. So what I would do is I would have the student walk along this line. Walk along the line parallel. Line parallel to the speakers. At a distance L from the speakers. Use the sound level meter. And determine where your max and mins are. Location of max and mins. It probably should say maximum sound and minimum sound, but you know what I'm talking about. Alright, so let me make sure I didn't lie there. I said set speakers a fixed distance D apart, determine a line parallel to the speaker line and the distance L away. Walk along the line with sound meter and check for max sound, measure distance Y. Okay, so that's pretty much what I said. Alright, then it says, using equations, show explicitly how you would use your measurements to calculate the frequency of the sound. Alright, so then I said, well, M lambda is equal to D Y over L. So I would go for the first one. I don't know the wavelength. I would know the D because I would have measured that. And I would get the Y and the L from my measurements. So my wavelength would be dy over L, but they want, I believe, the frequency, right? So then once I got the frequency, I would say, well, the speed of sound is equal to frequency times wavelength. So I would know that this would be 340, because that's what it tells me. My frequency is what I'm trying to find. My wavelength is going to be dy over L. So frequency is really equal to 340 meters per second times L divided by D over lambda. I mean D times Y, sorry. So there's my frequency. Alright, so now it says for part E, if the frequency is decreased, okay, explain how this would affect your measurement. So if you go back here and look at it, if my frequency is decreased, this stays the same and this stays the same, but that y is going to change. They are going to be inversely proportional. So what I'm trying to say is that y times f would equal all of this constant over here, because it's still the same speed of sound. You're still walking that same line, L distance away. The speakers are still D distance apart. So the only thing that changes is your frequency. Well, if the frequency went down, this should go up. Okay? All right, so let's clean that up, and then we'll see if we can go down and do the last one. So I'm going to pause for a minute. Okay, this should be our last one. Let's see what it says. In a classroom demonstration, a beam of coherent light wavelength 550, so there's our lambda, is incident perpendicular onto a pair of slits. Each slit has width is 1.2 times 10 to the minus 6, and the distance between them is that. Classroom observes that the length is 2.2 meters. And that's what it looks like. So we need to find the frequency of the light. Well, this is pretty easy. Speed of light is equal to frequency times wavelength. So 3 times 10 to the 8th meters per second divided by 550 nanometers will give me the frequency. And when I got the frequency, I believe that my frequency was 5.45 times 10 to the 15th. 10 to the 14th, sorry, hertz. So there's my frequency. That wasn't any big deal. All right, then it says, B says, calculate the distance between two adjacent dark fringes on the screen. So I said, oh my goodness, they want dark. So I'm going to have to do a half of a wavelength out of phase. So I found my first one. I said 0.5 times my wavelength of 550 is equal to D, which was given to me as 1.8 times 10 to the minus 5 over, well, the distance between those two is going to be 1.2 times 10 to the minus 6 over 2.2 meters. So, no, Miss Walker, this should have been my X1 that I was looking for. My bad. So that's the first distance. So when I solve that, I got x1 to be 0.0336. All right, now I want to go 1.5 wavelengths out of phase and do the exact same thing. It's equal to my 1.8 times 10 to the minus 5 meters. x2 is what I'm looking for now, over 2.2 meters. So x2, when I did it, was 0.101. So the distance from x1 to x2 is going to be 0.101 meters minus 0.0336 meters. So that y, that we call that value usually, is going to be 0.067 meters. That's what Part B wanted me to find. Okay, and then Part C said, oh, there wasn't a Part C, so we're done. Yippee skippy!